In this video, we're introducing the idea of a power series. And simply put, a power series is an infinite series that has powers of x in it. In other words, it's going to be a function of x. And the simplest type is like this. And in this expression, the c's are constants, and then I have increasing powers of x. Now, certainly, I would expect such a thing to converge if x was very small, since larger powers of a small thing would be even smaller. And so when x is very close to 0, this converges, and as a result, we call it a power series centered at x equals 0. Now I can generalize to a series that would be likely to converge at some other value of x. And I can see that if x is very close to a in this series, then x minus a is a very small thing, and higher powers of a small thing get closer and closer to 0. And as a result, we say this power series is centered at x equals a. And then real quick, we can talk about the possibilities for convergence of such a series. One possibility is the series converges only at x equals a, in which case it would clearly be convergent because the series would just be a sum of zeros, so it would converge to 0. Another possibility is that it converges for all x. And later on, when we get into talking about Maclaurin series and Taylor series, many of those will be in that category. And then a third possibility is that the series converges just for a range of x values. And so I said for x such that the absolute value of x minus a, that means the distance between x and a, is less than some value r. This r is then called the radius of convergence. And again, if x is within a distance of r of that center point a, then you would have a convergent series, and if it's outside of that, you would have a divergent series. So following up on part 3, we could also write this range of x values as an interval. So I'm talking about all the x's that are within a distance of r from a. So the interval for that would be a minus r to a plus r. And that gets a special name. We call that the interval of convergence. All right, there's one subtle point left over, and that is we don't know whether or not such a series converges at the endpoints of the interval of convergence. You have to test those individually. And in the example we're about to do, we're going to do that at the end of the problem. So let's move on to our example. We're given this infinite series that has powers of x in it. So the sum of 2x all to the n power over n. And we're trying to get the interval of convergence for this thing. So the standard attack here is to use the ratio test. Just a quick reminder, that's where we take the limit as n goes to infinity, the absolute value of the ratio of the n plus first term to the nth term, and we compare that to 1. And if it's less than 1, we have convergence. If it's bigger than 1, divergence. Equal to 1, the test is inconclusive. So let's set up the limit. The limit is n goes to infinity, absolute value. And then I'm going to write down my n plus 1 term. That's 2x to the n plus 1 divided by n plus 1. And then I divide by the nth term, which is the same as multiplying by its reciprocal. So n over 2x. Now I clean things up a bit. 2x to the n plus 1, I could split off a 2x out of that and cancel it with the 1 in the denominator. And I end up with the limit as n goes to infinity, absolute value of 2x times n over n plus 1. Now one critical point here is that the x is a constant with respect to the limit. Well, the 2 is as well. And so I can take the absolute value of 2x out in front times the limit as n goes to infinity of n over n plus 1. And those are positive, so I don't have to worry about absolute value bars on those. So when I take that limit, I could do it by dividing the top and bottom by n, or I could do it less formally by remembering the highest power of n will dominate in a sum or a difference, meaning the denominator is becoming approximately n. Those n's cancel and give me 1, and the limit of a constant is just that constant. So I have absolute value of 2x times 1, which I'm not going to write. And what I'm trying to do here is find the x's for which the series converges. And the series will converge if this limit from the ratio test is less than 1. So the absolute value bars either leave the 2x alone, or they multiply it by -1, depending on whether it's positive or negative. From the top equation, I end up with x is less than 1/2. And from the bottom equation, I end up dividing by -2 flips the inequality. X is greater than -1/2. So x has to be less than 1/2 and bigger than -1/2. And that means my interval of convergence is -1/2 to 1/2 as kind of a first guess. I still have to check the endpoints. And I could say the radius of convergence. That's just the distance from the center point out to the ends of the interval. That's 1/2. Okay, let's check the endpoints. If I plug in -1/2 for x, my series becomes the sum as n goes from 1 to infinity of -1 to the n over n. So 2 times -1/2 is just -1. Well, I recognize this immediately as the alternating harmonic series, and we've already proven this converges. If I plug in x equals 1/2, you might see what's coming. 2 times 1/2 is just 1, and 1 to the n is just 1, so I have just the infinite series, n equals 1 to infinity of 1 over n. Well, that's the harmonic series, which we showed using the integral test, diverges. And I suppose that means our real interval of convergence with the endpoints corrected should have one side closed. And these are all my x values for which the power series converges.